this lesson, we're going to talk about composite functions and combining functions, or having combinations of functions. The first thing that we want to look at and deal with is how we go about finding the domain of a combination or a composite function. And when you do this, you want to keep in mind that in the set of real numbers, there are only two things that we cannot do. We cannot divide by 0, and we cannot take the square root of a negative number. So unless your function has one of these two occurrences, your domain will always be from negative infinity to positive infinity. We will be able to use any of the numbers. But if you have an expression where you have a variable in the denominator, then you'll have to limit your domain in that x cannot be 0, or the denominator cannot equal 0. Or if you have a square root, then you have to limit yourself to positive numbers under that square root. So we're going to look at some problems and see how we would go about figuring up what our domain of these problems would be. So let's start with f of x is equal to x squared plus 3x minus 17. Now, when we want to consider if this domain is limited, what we look for is there a variable in the denominator, so that our denominator might be 0? Well, our denominator for all of these is 1. So no, that's not true. We don't have that occurrence. Or do we have a square root? Well, we do not have any square root here. So our domain would be from negative infinity to positive infinity. We're going to be able to consider all real numbers. Now, if our function was g of x is equal to 5x over x squared minus 49. Okay, we want to consider our domain. Well, in this case, we have a denominator, and we know that we cannot have a denominator of 0. So as we limit our domain, we need to think, well, what would make x squared minus 49 equal to 0? Or we can say it cannot equal 0. Well, if we solve this, we would add 49 to both sides. So x squared cannot equal 49. And then taking the square root of both sides, x cannot equal plus or minus 7. So we're going to have to limit those two numbers from our domain. We're not going to be able to use positive 7 or negative 7. We can use all of our other numbers. If we think of our number line with negative 7 and our positive 7, we can use all numbers below negative 7. We can use all numbers above negative 7 until we get to positive 7, and then we can use all the positive numbers above negative 7. So we would write our domain as negative infinity to negative 7, negative 7 to positive 7, and 7 to positive infinity. So we limited our domain. Let's take the function that h of x equals the square root of 9x minus 27. Well, as we start looking at this, we have a radical. We know that what's under the radical has to be greater than or equal to 0. So that's what we're going to do. We're going to say 9x minus 27 has to be greater than or equal to 0. It can't be a negative number. So if we'll add 27 to both sides, Add 27 to both sides. And then divide both sides by 9. We're going to have that x is greater than or equal to 3. And so that is our domain because that's what those numbers had to be. We didn't word this as what it couldn't be, but what it would need to be. So our domain's going to be 3 to positive infinity. Okay, we could have a function of f of x is equal to 1 over x plus 8 plus 3 over x minus 10. Now what we're wanting to figure up is what our domain would be here. Well, in this case we have two fractions, and so we have to consider each one. If we take the first one, x plus 8 cannot equal 0. So x cannot equal negative 8. And from the second one, we know that x minus 10 cannot equal 0. So x cannot equal 10. X can be anything else. And so if we think of our number line, we can have everything up to negative 8. So negative infinity to negative 8. We can have everything between negative 8 and 10. And we can have everything greater than 10. So from 10 to infinity. And so we would have limited our domain. It can be any values except at negative 8 and 10. It can be all the other values. If we had one with a sum of radicals, say h of x was equal to the square root of x minus 2 plus the square root of x plus 3. We have to consider each one. If we take this first one, well, x minus 2 has to be greater than or equal to 0. So x has to be greater than or equal to 2. If we take our second one, x plus 3 is greater than or equal to 0. So x is greater than or equal to negative 3. Now, it has to be both of these. Our domain is it's got to be what's in this one and also in this one. So if we looked at that at our intersection, then this one says x is greater than 2. So we would graph that as everything greater than 2. This one is everything that's greater than or equal to negative 3. So what we want to know then is where they overlap, and they overlap at all the points that are greater than 2. So our domain would be 2, infinity. And let's look at one last one where we're finding the domain. In this case, we're going to have a complex fraction. So we have h of x is equal to 5 divided by 4 over x minus 1. Now, this may look fairly strange, but what we know is that our denominator cannot be 0. Now, we know from the very beginning that this denominator cannot be 0 because no denominator can be 0. So we're going to limit that x cannot be 0. But then we have to look at this bigger denominator, and it can't be 0. So we're going to have 4 divided by x minus 1 cannot equal 0. Now, to solve this, we need to get us a common denominator. So we would have 4 over x minus, this is 1, so our denominator would need to be x. We'll multiply 1 times x, and then we multiply the numerator by the same thing. So we have 4 minus x over x cannot equal 0. Now, we've already said that the denominator can't be 0, so now to be a fraction to be equal to 0, the numerator would have to. So we'll set our numerator, 4 minus x cannot equal 0. We could add x to both sides, so 4 cannot equal x. So x can't be 0 and x cannot be 4. It can be all the other numbers other than 0 and 4. So it can be from negative infinity to 0, from 0 to 4, and from 4 to positive infinity. So you do need to be able to take a function and determine what its domain would be, what values you're able to use. And if you will remember, it's easier to think of what it cannot be. If you have a denominator, it cannot be 0. If you have a radical, then what's underneath it has to be positive. We can't take square roots of negative numbers. We want to then look at combining functions and how our notation for that. We're going to have it written that f plus g of x, this is the same as f of x plus g of x. We're simply adding two functions together. If we have f minus g of x, then that means we want f of x minus g of x. If we have f times g of x, then this simply means our function f of x times our function g of x. And then we might have where we have f divided by g of x, which means that we're wanting f of x divided by g of x, provided that g of x does not equal 0, because we can't divide by 0. So these are our operations. We're simply going to be adding our functions together, subtracting them, multiplying, and dividing them. So if we start out with the functions that f of x is equal to x minus 5, and g of x is equal to x squared minus 1. Okay, we want to find out what f plus g of x is. Now, first of all, let's look at our domain. There's nothing that's going to be limited in our domain for this function. There's nothing that's going to be limited in our domain for this function. So our domain for the combination would be the same thing. Would be negative infinity to positive infinity. Now, what this means is f of x plus g of x, which would be x minus 5 plus x squared minus 1. Well, removing our parentheses, then we can go and combine like terms, and I'm going to put this in descending order, so I'll have x squared plus x minus 6. And that would be our combination of that. If we took those same two functions and we wanted f minus g of x, then that means we wanted f of x minus g of x. Well, f of x was x minus 5, and g of x was x squared minus 1. Now, it's very important that we put our g of x in parentheses, especially. We need to put them both in parentheses, but especially we need to put our g of x in parentheses because we're going to be subtracting. So as we remove those parentheses, we'll multiply by negative 1. Then we can combine like terms and put this in descending order. So plus x minus 4. If we want f times g of x, and on all of these, our domain is still from negative infinity to positive infinity. But this means that we want to multiply f of x times g of x. Well, f of x was x minus 5. G of x was x squared minus 1. So in multiplying these, we will use our distributive property. So we will have x cubed, then x times negative 1, negative x, negative 5x squared, plus negative 5 times negative 1 is positive 5. If we rearrange this so that it's in descending order, then we would have x cubed minus 5x squared minus x plus 5. And again, our domain would still be from negative infinity to positive infinity. Now, if we went to our division, f of x divided by g of x, okay, that would mean that we have x minus 5 divided by x squared minus 1. Now, before we go on, we're going to have to limit our domain. And that means that x squared minus 1 cannot equal 0 because it would be in the denominator. Adding 1, x squared cannot equal 1. Taking the square root of both sides, x cannot equal plus or minus 1. So our domain on this one would be limited. As far as any of the computation, we're not going to be able to do any simplification for this problem because we can factor the denominator, but there's not going to be any common factor. So our domain then would be from negative infinity to negative 1, from negative 1 to 1, and from 1 to positive infinity. So we can take our functions then and we can add, subtract, multiply, or divide. Let's look at a couple of different functions and do some of our operations with these. Let's take that f of x is equal to the square root of x minus 3, and g of x is equal to the square root of x plus 1. Okay, we need to go through and consider what our domain is. Well, for this one, x minus 3 has to be greater than or equal to 0, so x is greater than or equal to 3. For this one, x plus 1 has to be greater than or equal to 0, so x has to be greater than or equal to negative 1. Now, we need to go where these two overlap. And as we do that, then the only numbers that we can use, if we deal with what's greater than negative 1 and what's greater than 3 or equal to, then the place where they overlap is from 3 to infinity. So 3 to infinity would be our domain. Those are going to be the values that we can use for these two functions. So we can't use numbers like 2 because 2 would make this part negative. So if we go to add and we want f plus g of x, means we take f of x, which is the square root of x minus 3, and we're going to add to that g of x, which is the square root of x plus 1. And there's not any simplification that we can do, so that would be our final answer. If we want f minus g of x, we would do the same thing. It would simply be we would be subtracting them. If we want f times g of x, then that means we want the square root of x minus 3 times the square root of x plus 1. Well, when you multiply two radicals, you multiply the numbers that are underneath the radicals, or whatever's underneath. So we're going to have to multiply this. This is going to be the same as the square root of x minus 3 times x plus 1. And we could multiply that out. We've got x squared plus x minus 3x minus 3. Combining our like terms, we have x squared minus 2x plus 3 minus 3. And that would be the combination of those two functions where our domain is from 3 to positive infinity. If we were to want f divided by g of x, then that would be the square root of x minus 3 divided by the square root of x plus 1. Now, we've already limited our domain from 3 to positive infinity. But on this one, we're going to have to limit our domain just a little bit more because our denominator can't be 0, and so x cannot be negative 1. Well, let's just think. Our domain was from 3 to positive infinity, so was negative 1 in that domain anyhow? No. So we're okay as far as that part goes. And we could go through and rationalize, but right now we're just mainly looking at the domain. Now if we went g of f of x, where we were taking g of x, which was the square root of x plus 1, and dividing it by the square root of x minus 3. And we could go through and we could rationalize, but notice on this one, our denominator, can't be 0, so that means that x cannot equal 3. Well, up here in our domain, we included 3, so for this problem, our domain would need to be 3 to positive infinity, and we cannot include the 3 because it would make that denominator 0. So this is working with our combinations where we're adding, subtracting, multiplying, or dividing. You want to make sure that you get your domain and then just do your operation. We also have what's called compositions of functions. And this is where you've got a function of a function. And examples of when you would actually use this, if you'll think about the way you get paid for a job. You get paid by the hour, and so you would do that function, your wages depending on how many hours you worked. Then you take that answer and that determines then how much tax you pay. You don't know how much tax they're going to take out until you know how much money you've made. So that's an example of a composite function where you're taking a function, working it, and then you're substituting it into another. And we have two different notations for this. We have f of g of x. And this is a little circle, kind of looks like the word fog, but it's a small circle, not a 0. But this is one way, and it's read f of g of x. And you'll often see it written this way. Another way that might be a little bit easier to understand is f of g of x. Now what this helps you understand is you're taking the function f, and wherever there's an x, you're plugging in the function g of x. So we're putting our function into our function. we'll also have to consider our domain on this. And when we do, then if we're looking at this, then X is the domain of G, of the function G, whatever that is. You have to look at whatever the function G of X is and determine what its domain is. So X is the domain of G, and G of X is the domain of F, the function F. So what we're going to have to do is consider, well, what happens if we plug our function into it? Again, we're going to just be looking at ways that would make the denominator 0 or would make what's underneath the radical a negative number. So let's look at some, and it'll be a little bit easier to see what we're talking about. Let's look at the function where f of x is equal to 5x plus 6, and g of x is equal to 2x squared minus x minus 1. Now for both of these functions, our domain would be negative infinity to positive infinity. We have no denominator and we have no square root. So our domain in both cases would be negative infinity to positive infinity. So when we start doing our compositions of these, our domain will be the same. None of these were limited. So if we wanted f of g of x, and a lot of times I like to write it f of g of x. Let me write it a little better there. F of g of x. I like that way a little bit better than the FOG of x. But you may use either one, and you're going to see it both different types in the books that you would be using. So this means we want to take our function f, and wherever there's an x, we're going to plug in our function g of x. So we would start out, we're going to take our function f, so we've got 5. Now wherever there's an x, we're going to plug in g of x. So we would plug in 2x squared minus x minus 1 plus 6. And then we simply simplify it. So we would have 10x squared minus 5x minus 5 plus 6, which gives us 10x squared minus 5x plus 1. And we have our composition of our function where we would take one function, substitute it in to a different function, and come up with a new value. And we might want to take this and find a specific value. Maybe we want to find f of g of 2. Well, we just found out what f of g was. So what we're going to do now is to take our function, wherever there's an x, we would plug in 2. So 2 squared would be 4, times 10 would be 40, minus 10 plus 1 would be 30, plus 1, 31. So we can evaluate our composition of our function. Now, if you go back, just to help you see what we've done, if we went back to our original function, we want f of g of x. What that means is we wanted to be able to evaluate g of 2 and then take that answer and put it into f of x and evaluate it. And let's see, would we get 31? So if we found g of 2, That would be 2 times 2 squared minus 2 minus 1. So that would give us 4 times 8 minus 2 minus 1 would be 5. Now, if we went to our function f and wherever there was an x, we plugged in 5, we would have 25 plus 6, 31. And you can see we would get the same answer if we do it the long way, taking a function, finding an answer, and then plugging that answer in, or if we do the composition of the functions and come up with a new equation. And if you were having to do these over and over again, that's definitely what you would want to do. Now we can also do g of f of x, which would mean another way g of f of x. This means take the function g and wherever there's an x, plug in the function f of x. Now our domain was still the negative infinity to positive infinity. But what we're going to do on this problem is we're going to take our g of x, which was 2x squared minus x minus 1, and wherever there's an x, we're going to plug in f of x, the 5x plus 6. And let's see what we get there. So when we want this, then our g of x was 2x squared, so we want 2. And what we're going to do is plug in our f of x, which was 5x plus 6. Then minus x, 5x plus 6, minus 1. Okay, if we square 5x plus 6, you can use the pattern. You can go off to the side and do 5x plus 6 times 5x plus 6. Work that out. But you're going to get 25x squared plus 60x plus 36 minus 5x plus 6 minus 1. Distributing, we have 50x squared plus 120x plus 72 minus 5x plus 6 minus 1, which gives us 50x squared plus 115x, and that would be 78 minus 1 plus 77. And I made a mistake back here. I'm sorry. I didn't distribute my negative. So this should be a negative 6. Let me go through and change that. So that's a negative 6. So we ended up with 72 minus 6. Let me change that one. And that's going to change this number. So 72 minus 6 minus 1 would give us 65. Okay. Always have to watch that distributive when you've got a negative sign. And our domain would be from negative infinity to positive infinity because, again, we had nothing that would limit our domain. All right, let's look at two different functions. Let's say that we have f of x is equal to 4 over x plus 2, and g of x is equal to 1 over x. Now we want to find f of g of x. So we're going to be taking the function f of x. Wherever there's an x, we're going to plug in g of x. Now what we said earlier on the domain was that first of all, you had to deal with the domain of x as a function of g. So if we look at this, we know that x cannot be 0. So we're going to limit that from our domain. Now we're going to take this value and plug it into our other equation. And so we would have to, first of all, we would have to see what would make this denominator 0. Well, if x equaled -2, this denominator would be 0, correct? And so when we look at that, then we're going to be plugging in 1 over x. So 1 over x cannot equal -2. Because if it equaled -2, then our denominator on our f of x would be 0. So if we take this and let's just multiply both sides by the x, we're going to have 1 equals -2x. Dividing by -2, then we get -1/2. X cannot equal -1/2. If x equals -1/2, then this denominator is going to end up being 0. So we have to first of all just see what this one can't be. It can't be 0 anyhow. But then we have to see, well, what would make this denominator 0? Well, if x were 2, since this is what we're plugging in for x, then that's what we deal with as it cannot equal 2. So our domain, it can't be 0 and it cannot be -1/2. And those are the only things that would limit it. Now if we go through and work this, then we're taking f of x. Wherever there's an x, we're going to plug in g of x. So it would be our function. We need to get a common denominator for our denominator, which is going to be x. So x times 1 is x, 2 times x. So that would be 2x over x. Or that would be 1 plus 2x over x. And to divide by a fraction, we multiply by the reciprocal. So this is going to be 4 times x over 1 plus 2x, which gives us 4x over 1 plus 2x, provided that our domain is from -infinity to -2, or -1/2, excuse me, from -1/2 to 0, and from 0 to positive infinity. So we had to first of all think what could be in our domain here, because that's what we would be plugging in. So x couldn't be 0. Then we had to go and consider what x could not be here. Well, if x were -2, then this denominator would be 0. But this is what we're plugging in, so we had to figure out what would make this -2. And so that would be if x were -1/2. And you can see once we got our composite function, you can see how the denominator here could not be -1/2. And but we still also have to eliminate the 0. Let's just go through that same one. Let me go back to it. Maybe, okay, here it is. And let's instead do g of f of x. Well, in this case, what we have to do is we have to consider, first of all, our f of x and what it could not be. Well, if we go back to that, x could not be -2, because that would make our denominator 0. And then we're going to be plugging it into g of x. Well, that denominator can't be 0, so we have to consider what would make that whole function equal to 0. What would make 4 over x plus 2 equal to 0? 4 over x plus 2 cannot equal 0. And as long as we have a numerator, there's no variable in the numerator, there's no way that that fraction could ever equal 0. So the only thing we're having to limit is that x could not be negative 2. The only way a fraction can be 0 is if the numerator equals 0. So x cannot be negative 2. And then in this case, we would take our function, and which was 1 over x. G was 1 over x, and wherever there's an x, we're going to plug in f of x, which was 4 over x plus 2. To divide by a fraction, you multiply by the reciprocal. So we'll multiply by x plus 2 over 4, which would be x plus 2 over 4. And our domain would be, it can't be negative 2, so it would be negative infinity to negative 2, and from negative 2 to positive infinity. Okay. And if we looked at f of x equaled x squared plus 4, and g of x equaled the square root of 1 minus x. Okay, we're going to find our composition f of g of x. So we're going to start with g of x and figure out what value of x would make g of x 0 or would not be able to use. Well, we know that 1 minus x has to be greater than or equal to 0. So negative x is greater than or equal to negative 1. Dividing both sides by negative 1, we would have to switch our inequality. So x has to be less than or equal to 1. Then we go to our function f. Is there anything that we would have to limit from our domain on it? And there's not, because there's no denominator, there's no radical. So this is the only thing that's going to limit our domain, is x has to be less than or equal to 1. So we're going to take our function f. Wherever there's an x, we're going to plug in g of x. So 1 minus x squared plus 4. When we square the square root, we get rid of the radical. And so we end up with 5 minus x. And our domain then was from negative infinity to 1. We could include the 1 in this case. Okay, the last thing we're going to look at real quickly is talking about decomposing a function. And this might be where you see a composition and you want to come back with, well, what could our function have been? What would have given us this function? If we have h of x equals the square root of x squared plus 5. Okay, we want to think the innermost part. And so we might think this innermost part was our g of x, because that's the first thing that we would be doing. So if we let that innermost part be g of x, so g of x is equal to x squared plus 5, then we can see that our f of x would have had to been the square root of x. So if we had our f of x was the square root of x, and then we substituted g of x into it, then this would be the composition that we would have gotten if we had found f of g of x. And that would have turned out then to be our square root of x squared plus 5. We took our function f, wherever there was an x, we substituted in g of x. And so we were able then to come up with the composition that would have given us this function, this new function, h of x. Looking at one more, if uh, if h of x is equal to 1 over 2x minus 3. Again, you want to look at the most common part of the function, or the complicated part, which is what's underneath the square or the fraction bar. And so that would be your g of x. That's what we're substituting in. So our g of x would have to be 2x minus 3. Now, when we substituted it in, we put it underneath the fraction, so that meant that f of x would have to be 1 over x. So when we took f of g of x, we took our function f of x, and wherever there was an x, we substituted in g of x. And so we're just simply taking apart the functions. So you should be able to combine functions, do compositions of functions, and be able to take a composition apart.